Okay, so I would like to introduce XenoKovah, who is one of the best hardware hackers that I know, and it's really exciting to have him give us a talk about Bluetooth printing.
All right, hello everyone, I'm XenoKovah. And yeah, so Bluetooth tooth printing is what we're going to be talking about today. We're just Bluetooth printing. So first, the obligatory About Me slide, in which I say what I'm talking to you about today is not my whole deal. In fact, it's not even the majority of my whole deal. It's the minority of what I do. The majority of what I do is I make free classes and I put them online. So free as in freedom, free as in beer. So basically, I run this nonprofit called Open Security Training 2, because Open Security Training 1 was a hobby project that I started back at MITRE when I was 2011 or so. But 2021, we relaunched as Open Security Training 2, and now it's an actual dedicated full-time project for me. So 25% of my time is then just doing hobby research and anything that I can't put under the nonprofit umbrella. But also, I use it to do this research, which is just a Trojan horse just to get this slide in front of people at conferences. ShmooCon let me talk about open security training last year, but you could only do that so long. Eventually, you have to do some research and put that in front of people. But I just want to say it's not just me at Open Security Training. It's all of these people giving you all sorts of cool free classes on C++ reverse engineering, UEFI, BIOS, Windows exploits, all kinds of cool stuff. And actually, we have a class right now in beta on TPM, Trusted Platform Module. So that'll be released in about a month or so. Now, to the point of this talk, what do I want to know in my research? I want to know what Bluetooth chip is inside any given device that I see broadcasting Bluetooth. So I've got a bunch of random Bluetooth devices. I want to know which silicon is inside of that. Now, why would I want to know that? Well, because I want to know if it's vulnerable to over-the-air, wireless, arbitrary code execution exploits. So Texas Instruments, back in 2018, ARMIS found a vulnerability where they send a magic packet, get arbitrary code execution, specifically on Texas Instrument chips. In 2019, researchers at the Technical University in Darmstadt, Germany, found a vulnerability in the Broadcom chips that applied to Apple devices and Macs and iPhones and all that kind of stuff. In 2020, my wife, Veronica Kova, presented at Black Hat that she had found vulnerabilities in Texas Instrument chips and also Silicon Labs chips. So all of these types of vulnerabilities are not just like logic bug type things that you heard about, perhaps if you watched the talk about Apple keyboards and keystroke injection and stuff like that at the conference. These are just send magic packet, get arbitrary code, take over the device. So those are cool, but we want to know, like, where does that apply? So I should say, like, you know, when my wife Veronica did her talk at Black Hat, we didn't make a whole big deal about it because the net result is great. We have arbitrary code execution. Where does that work? How does that apply? What is the impact? And the answer is we don't know. So we don't know where all the Texas Instrument chips are used, what kind of devices. I showed you the picture earlier. I know it's used on, like, you know, Teslas and stuff like that, but those are sort of like ad hoc results of like onesie twosie. Ecosystem-wide, nobody knows. Once you have a vulnerability in a chip, no one knows where all it's used. So this is kind of what I really want to know. I want to know a version print that can precisely tell me, I see a Bluetooth device beaconing some sort of information. I want to know, okay, it's this particular chip at version 3, and I know that's got the vulnerability or it doesn't have the vulnerability. That's what I really want to know. But I'm going to share with you a whole bunch of other information that I can get that, you know, tries to get me close to that, because you'll see that very often I can't get exactly that information, unfortunately. So you got version prints, like say some chip at some version. You've got chip prints that tell you it's exactly this chip, but I don't know which version of firmware it's running, so I don't know if it's vulnerable or not. You can have chip maker prints. You've got many chips. Maybe not all of them are applicable. Like for my wife's Texas Instruments thing and the ARMIS Texas Instruments thing, it was only some subset of the Texas Instruments silicon that applied, because some silicon had diverged and they had baked different code into their ROM and others had not. So basically, one chip maker, many chips, many versions for each chip. Some have vulnerabilities, some don't. And then there's an interesting thing in the Bluetooth ecosystem called module makers. And these are basically what I call manufacturers in the middle. So you've got a chip maker like Realtek. They go off and sell their chips to a module maker like AI Thinker. And the module maker then sells a whole bunch of Bluetooth modules. And these are basically little tiny PCBs that have the Bluetooth chip, but they also have things like the antenna and the crystal and stuff like that. And the basic point is that these are already FCC approved because you have to go through regulatory authorities to transmit wireless information in this country and most every other country. And so there's a value add to basically say, I don't need to have RF engineers figure out my particular antenna design and power amplification and things like that. I'm just going to buy something that's already pre-approved and slap it on my board. So that's why module makers exist. But once there are these module makers who make many modules with many different chips, like these are all Realtek chips, they tell us which chip in that row, then the question is which products do those go out to, right? Again, nobody knows. Like honestly, even the Realtek won't know where all their chips are used. So you've got the module makers, but then if we come at it from the other direction, you've got product makers. And at the time I made these slides originally, there were 3,330 registered product makers with the Bluetooth special interest groups. So there's more than that by now, and I expect there's probably also product makers who don't bother, just for really small devices, they don't bother to register with the Bluetooth SIG. So you got many product makers, each product maker makes many products, and for each product there should be some sort of one-to-one relationship between this product has this chip, and that's what we got to find out. We have to discover, does product 1 have chip 1 and product 2 goes through a module maker and that has chip N? All of this is kind of the information that we can discover and try to tease out about devices. And then furthermore, something that can help us is that amongst the module makers, they're going to have very specific chips that they use. So, that AI thinker, they were using Realtek, but some other module maker, they may actually offer modules from many different things. Like they'll sell a Nordic chip and a Texas Instrument chip and a Realtek chip, something like that. So, but basically, by knowing something about these module makers, you can say, well, I know that if I could figure out which module maker it is, then I could know that, well, they only use chip maker, 1's chips and these 2 chips. And so even that gets me closer to what I want to know. It gets me closer to, are these vulnerable chips? So unfortunately, this is what I want. I really want to know just, does it have the vulnerable firmware version that has a known exploit? And this is what I mostly get. And so we'll be digging through a bunch of this data, but we will see some instances where we get chip prints where it gets us really close, but like this is a lot of the kind of information we get and like where can we pull this out of the Bluetooth packets and stuff. So my terminology for the purposes of this talk is that BTC is not Bitcoin, it's Bluetooth Classic, BLE, Bluetooth Low Energy, and BD-adder, Bluetooth Device Address. This is like a MAC address. So when my wife did her Black Hat talk and she had, exploits, I said, that's great, but eventually we're going to want to figure out, like, where does this apply? And so back then in 2020, I started just collecting naivest way possible, just run Linux on a Raspberry Pi, run Bluetooth Sniffer on there, and just collect all the data. And so then I did that for like 3 years, and then I only last year started getting around to like looking at the actual data. So I've got another talk where I talk about all the various anecdotes and stuff like that, cool, weird things I see, like driving through Chantilly, Virginia, there's some, traffic, and like Caterpillar heavy equipment has Bluetooth keyless ignitions and stuff like that. Like cool stuff that I just see driving around. That's a different talk. This talk, we're going to say, okay, now I've got all these millions of data points. What can I do with that? What can I tease out of that about what I really want to know, which is where can we use these exploits? So last May I started digging into this. This is like just to give you a sense of things. We'll talk about the breakdown of these types of BD-adders in a second. But basically you can say I have about 75,000 Bluetooth Classic devices, which makes up 1% of my data. So that's why there's been an explosion in Bluetooth hacking since about 2013. That's when Bluetooth Classic when Bluetooth Low Energy sort of hit the scene. And Bluetooth Low Energy just really ramped up really quickly, whereas Bluetooth Classic, it got kind of stuck in certain niche use cases. And I've got about 8.5 million Bluetooth Low Energy things, and we'll break down those different types in a second. So when it comes to tooth printing, so this identification of the things, there's 3 ways you can go about it, and what I call passive, mostly passive, and active. So passive would be the notion of you just set up a sniffer. You are not going to actually send any packets, you're just going to listen to the air and hear what you hear. Now, that's good from a stealth perspective, like if you just want to know like what's talking right now, like I'm kind of curious, let's go ahead and run a sniffer right now. Yeah, so we've got about, in like 20 seconds, I see like about 1,100 devices, like passively, there's about 1,100 devices in this area right now, 1,200 now. So you could just sniff, and if you found something that was sufficient for you to know, like, oh, that particular address is exploitable, then you could just sniff and exploit. Great, no one's going to see anything. I distinguish that from there's then mostly passive. Mostly passive is you're going to send some packets, but these are going to be basically what you would say are natural packets. And so anytime you go into the like Bluetooth settings on your phone or something like that, and you say like what Bluetooth stuff is there, your phone will naturally send a variety of query packets out to say like who's there right now, because it's trying to find, you're trying to pair with some device, your keyboard, your headphones, whatever. You're trying to pair with some device. Your phone, your Mac, your desktop, it sends out a bunch of stuff to say who's there, and then it gets responses back. So this is mostly passive in the sense of you didn't do anything special, this is just natural stuff. And so I'm making this distinction to say if anyone ever wants to make anomaly detection system to say I can see someone's like scanning for bad Bluetooth things, we've got a threat actor in the area. Well, this is just like natural behavior, so there's nothing suspicious about the mostly passive stuff. Active, on the other hand, is where you start whipping packets at people, like I happen to be doing right now to all of you with my Bluetooth device in my backpack. So I'm just whipping packets at all of you and saying, hey, what's your device response to this kind of packet? And so that is potentially anomalous depending on how weird you get with it. And as you'll see in this talk, getting weird is kind of the best way to get the information that you want. But so you're going to typically send custom packets and potentially malformed packets. All right, so I'm going to talk about a variety of tooth printing mechanisms, and I'm going to start with the easiest one, and then we'll talk about the more custom one, and then I'll work back towards some other ones. So tooth print by BD OUI, I'm going to say this is a passive technique. You can collect this information if you were being just a passive adversary. So BTC, Bluetooth Classic, BD Bluetooth device address, it's basically a MAC address like you're used to dealing with in Ethernet. You've got an IEEE organizationally unique identifier in the upper bits. It's usually 24 bits, but it could also be 20 or 12 bits these days. And so basically, this tells you something about the company that this particular device has assigned. So in Bluetooth Classic, these things never rotate. They're just like a static MAC address. They're fixed. They're set at manufacturing time, and you don't ever change them. So consequently, if Responics Inc., which sells devices that are like CPAPs, continuous positive airway pressure devices for sleep apnea. So it's a thing that blows air in your nose while you sleep. Responics, they are going to manufacture the device. They're going to say, hey, this is a Responics device. And then it's always going to say that forever, and I can always tell when there's Responics devices around. Bluetooth Low Energy, I'm going to hand wave for a second here and just say that there is a bit in the packet that says, is this a public address or is this a random address? If it says it's a public address, it's exactly like Bluetooth Classic. You've got an OUI at the beginning, and that's going to tell you something about the company. If it's a random address, then we've got three types. We've got random static, and that has the upper two bits are 1, 1, and the rest of it is just random static, never changes, but unlike a classic address or a public address, it doesn't tell you anything about the company. So you can't infer this is a Responics device or an Apple device or any other company's association. So it's random static. Great if your threat model is trying to track someone around the world, but not great if you're trying to figure out, which company or which chip maker this is associated with. Then we also have random private addresses, and then there's subdivided into random private resolvable and random private non-resolvable. We don't care about the details of those. I just want to point out the bits. There's 0, 0, and 1, 1. These are things like when you hear the statement of like the iPhone changes its Bluetooth address every 15 minutes, they're talking about a random private resolvable address, and the distinction is just it's not completely random. There's some sort of hash in there that has to do with two entities that know a key, and then they hash it, and then they can say like, oh yeah, I know you. So that's it. So back to my stats. What do I care about amongst these stats? I care about, for figuring out which company this is associated with, I care about those 75,000 Bluetooth Classic devices, because that'll directly tell me the company, as will the Bluetooth Low Energy public addresses, the 205,000. So here's the stats. You don't need to, there's nothing super interesting about them. All I want to do is start to introduce this convention of, I'm going to put little emoji icons here. Phone-related, car-related, audio-related, chip-related is the one we're really going to care about. If there's a chocolate chip cookie, that is a chip maker. And so down this row, we've got like Action Semiconductor. So I have devices where I've seen their traffic, and they say, based on their Bluetooth, this is Bluetooth Classic, based on their Bluetooth Classic address, I am associated with Action Semiconductor. Now, I don't think Action Semiconductor is actually making a bunch of consumer devices. I think that some consumer device makers are just lazy and they don't bother to overwrite the BD adder. Consequently, they're just using whatever it came with, and it came with their silicon vendor's BD adder. So that gives us a strong indication that probably these random devices that we see going around, those could have this exact silicon maker if we're interested in, if we had an exploit for that silicon maker. So you will see that my data is kind of car skewed. And if you look at one of my previous talks, you'll know that I like to put these sniffers on overpasses on 495 and let the cars drive underneath and collect the data. So my data is skewed towards cars. That's why Garmin's #1 here, because Garmin makes these like diesel GPS things, like the name is diesel. I'm pretty sure those are a bunch of trucker things, and so I get lots of data from truckers and cars and everything else. So skewed towards, audio entertainment systems, that kind of thing. And just the Bluetooth low energy thing, here we can see that the top one is actually Texas Instruments, a chip maker. Then we've got, some other things. We've got Silicon Labs, we've got Expressif, we've got T-Link, and so on. So basically this is just saying, this is the first traces of what I actually want to know, right? If I can say, this device that I'm seeing right now, just based on its Bluetooth address, which I can completely passively collect, has my company is of a silicon maker's company, then with high probability that is using that silicon maker's Bluetooth chip, right? And so there are some that also actually have module makers in there, and so that's where I was saying with that whole spread out, like this module maker, like AI Thinker, whatever it was called, they may only use like 2 pieces of Bluetooth silicon or 3 pieces of Bluetooth silicon. So once you know module maker names as well, you can severely cut down the 20 plus silicon makers who make Bluetooth chips down to just what that module maker uses. So I see some BD adder, I use an IEEE OUI database lookup, I see that it says it's a Texas Instrument one, and my assumption is that an OUI print equals a chip print for this purpose, and therefore it's probably using Texas Instrument silicon. Okay, tooth printing by link layer version information. This can be either semi-passive or active. So down at the lowest layers of the Bluetooth stack, like right above the physical layer, at the lowest layers, Bluetooth Classic has a protocol called Link Management Protocol, and Bluetooth Low Energy has its link layer control packets, so link layer protocol and then control packets and data packets. So amongst those two things, there are packet types for Bluetooth Low Energy, it's LL version indication, and Bluetooth Classic, it's called LMP version response. Those are 2 types of packets I can fire at your devices right now, and your devices with some probability will send me back information from these packet types, and it doesn't require any sort of pairing or bonding. So basically all of that rigmarole of like type in the code and that kind of thing that you associate with Bluetooth, not applicable here. This is all the like lowest level protocol that is like how you speak that protocol for setting up pairing and things like that. But off to the side, there's other packet types that are not the, hey, let's set up pairing, hey, let's exchange crypto keys. So the Bluetooth spec, quite frankly, is absolutely terrible. This is an excerpt from it, and this is it just telling me what the packet types look like. So this LMP version response, it tells me there's 3 fields in there, but it doesn't like tell me what the sizes are, what the contents are, or anything like that. It tells me you can send a version request, you can get back a version response. So thankfully, at least the low energy spec is a little bit more verbose. It's basically these 2 packet types, when they created low energy, they just said, yeah, let's reuse that same packet from Bluetooth Classic. That seems like that works. So it's all named the same, it's all the content the same. So you've got version number, 1 byte, company ID, 2 bytes, and a subversion number, 2 bytes. So I recognize that this could potentially, version numbers and stuff like that could potentially be useful for firmware version numbers, but I got kind of scooped on this point. So I said I only started like looking at this like last May, looking at my data, and then around September I accidentally stumbled upon this talk from Woot this past year, which didn't have a Bluetooth title, but I eventually found it, and I was like, oh crap, they realized that too. And I mean, it's an easy realization, it's just from the spec. But basically, in this talk, they were saying like, hey, we can put custom firmware onto ESP32 chips, and then we can, do sniffing from our watch, and that is cool. But they said like, hey, and, they had 1 slide and 1 tiny paragraph in their paper saying, by the way, there's this LL version indication type. We use this to fingerprint all the Bluetooth devices that we see. And so that's almost true, but it's really not sufficient. It's like a component of the larger toothprint. It's not sufficient by itself. They didn't offer any sort of proof that this could be used for fingerprinting, so I've got the data so I can take a deeper look. So we look at their specific example. They were seeing a MediaTek device at the time, and it had, a subversion number of 0. So I can look through all my data. MediaTek is company ID number 70, and then I can quickly see that the most common subversion numbers are 0, and this actually like dwarfs all the rest of the data. So that means like, okay, I saw a device that said like, I'm a MediaTek device, I have a subversion of 0, but is that sufficient for me to know that like it actually has a vulnerable and exploitable Bluetooth stack if I had some MediaTek vulnerability? Maybe, maybe not, right? It's just the only point here is it's not sufficient. Like that's too much stuff lumped in. It's not specific enough. You need to grab more data points to be more precise. It is not a one shot, one kill. So looking at my data, looking other MediaTek stuff, all of MediaTek stuff with a subversion of 0, it could be a knockoff iPad, it could be these bikes outside of an Italian hacking conference where I had been seeing these devices advertising for the longest time. I couldn't figure out what they were, and then finally I figured out here, it's bike locks. It could be a Nokia phone, or it could be a telematics unit for like shipping tracking and stuff like that. So all of these devices are MediaTek devices with subversion 0, so not precise enough by itself. But just to explain a little more, like what are the other fields of that packet type? The version number, that's pretty simple. That is just saying what spec version it conforms to, actually. So it's saying we were manufactured with an expectation that we would conform to Bluetooth spec 5. There are certain packet types and protocols and things, some mandatory, some optional, but it's just saying we hit this. So obviously the older the spec version, if it's saying like we conform to version 4.0, I think like 4.0 didn't even have some of the more secure like Diffie-Hellman elliptic curve pairing technology. So you could know immediately from that, oh, this is probably vulnerable to like older architectural vulnerabilities, and then go exploit those instead. You don't need an arbitrary code execution vulnerability in that context. The second field is then that company ID, 2 bytes. And here again, we just take the 2 bytes, look them up in a table, and now you can see that this is like an extremely high signal to noise ratio detector of this company ID, just happens to be a company that makes silicon. So we've got Broadcom. Apple mostly uses Broadcom, but they also describe their devices as Apple silicon if it's like an AirPods or something like that. So most of the big devices are Broadcom. Most of the small devices are Apple silicon, Apple custom silicon. Nordic, Qualcomm, et cetera, et cetera. Now, that's great. Those are almost all chip makers, and therefore, if I send these packets at you right now and I get the response back, I can probably tell what silicon your device is making, except that your device may not even respond. And so that's another problem with just assuming that, you know, without the data, that like this is good enough to fingerprint devices. So from my data, I only see 12% of the time that the devices actually respond to me. Now, my data is noisy and messy and not like taken in a scientific manner. Like I said, it's just 3 years of run Raspberry Pi in my backpack. But like I have a student that's now sort of looking at this from the perspective of most of the time I expect that these things will respond, but it's usually like low signal strength. So like my device right now could be like, see someone who's like 2 rooms over and it's trying to like fingerprint them, but the signal strength is so low that even if my packet gets to them, their packet may not get back to me. So we need to actually like assess this in the context of like signal strength to know how good it actually is at the end of the day. So same thing for Bluetooth Classic, mostly silicon makers, and I can actually tell you with like very high certainty that these onesies down here are almost all like bit flips where I get like corrupted data. So like I know for sure that G wearables is not the actual field, it's just a bit flip somewhere. Now Bluetooth Classic, we get a little better data. We've got 31% of the time the devices are responding to these low-level inquiries for information and giving us back good information about which silicon it's actually using. All right, and then just for completion, there's this subversion number, the 2 extra bytes in that packet type, and the vendor gets to make up whatever they want here. Now, when I read the spec here, it says subversion number field shall contain a unique value for each implementation or revision of an implementation of the Bluetooth controller. Now, I'm a firmware person, and when I read that, I was like, oh, it's going to change the version for each revision. It's probably a firmware number, right? But unfortunately, the silicon makers read that, and they said, oh, well, that should be a silicon revision number, right? At least, you know, so far, that's what I think they may be doing. So my hypothesis was this subversion number is going to be the perfect, precise, like, you know, on an Apple device with like a Broadcom thing. I'm going to like, you know, do a firmware update. I'm going to move to the newest version of macOS, and I'll see that subversion number is going to change, and then great, win. It gives me like signal about firmware version and exploitability. And at least for Broadcom, it's a very severe reject on that assertion. So digging around through, I just came across this sort of accidentally, like I wasn't even looking for this, but in the Blue2, which is the Linux stack, in their open source code, there's this packet.c. They've got Broadcom USB subversion table, so there's probably, like some of you may know USB stuff and tell me afterwards, but I don't know USB stuff, but maybe they have a subversion and it's being used the same way between USB and Bluetooth. But they've got this subversion table, and these are names that are essentially BCM for Broadcom, 43142A0 and 4314A0, blah, 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 blah. You can see A0, 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 A1, A2, B0, C0. These are basically, Broadcom is the manufacturer, 4335 is the chip, and C0 is actually the silicon stepping. So basically, they put out the first version of the chip, and eventually they find some bugs and they need to like actually revise it. So they go from A0 to A1. It's still basically the exact same silicon, but they fixed some bugs and they ran a new ROM and stuff like that. So this is like the most precise you can actually get with like which silicon is. It's the chip, but it's also the actual stepping of the chip. And then I remembered that there's this tool from TU Darmstadt in Germany called Internal Blue, and they have all of these firmware files. So they were, again, focused on like Apple and Broadcom, and so they basically, they have a system for like hooking the firmware and sending arbitrary packets with that. And if you look at their repository, they've got this big pile of firmwares in there. And you go through that and you see, oh, they have firmwares that are labeled like firmware 6109. And you go to the Linux source code and you see 6109 is actually a Broadcom 4335C0. So actually, basically, these subversion numbers, they use them in Internal Blue to say, let me check what the device says it is. Okay, great, I'm going to send it a custom firmware so that I can hook it to send arbitrary packets out of that Broadcom device. So yeah, this is a strong reject of my hypothesis of like these are going to be numbers for like firmware revisions for determining exploitability, but it is basically the perfect chip print because you can't get any more precise than silicon stepping numbers. So I said this is what I really want. I want version numbers. This is what I mostly get, like chip makers, Texas Instruments, and Silicon Labs, and so forth. But this right there was basically a perfect chip print. Now, if I can get these packet types back, it gives me exactly which chip this is. And also, I should say that those stepping revisions, sometimes the stepping revision is because of like actual security vulnerabilities and stuff like that. So a Broadcom, B0 versus a C0, a major thing, they may or may not have like actually fixed some exploitable vulnerabilities for me while I was at Apple. So subversion, does it imply firmware version? No. For Broadcom, weak reject for MediaTek, the data suggests that probably not because everything's clumped together with that subversion 0. But the key thing here is just this all requires actual like hands-on investigation. You can't just like scan the world and like infer like for sure whether it's true. You need to have a device, do a firmware update, see whether the version changes. That starts to tell you whether or not this is actually for this vendor being used in this way. All right, toothprint by link layer packet combinations. So here I just want to say that version information is the most obvious thing because I ask you the version, you give it me back. That's the most obvious thing. But if you think about what I'm trying to do here, you could relate it back to the notion of like Nmap and operating system fingerprinting. So if you're doing network security and you know that there's a device on your network, but you don't know what it is, and you say, Nmap, tell me the operating system. What Nmap is doing is it's creating a bunch of combinations of packet types. It's sending those packets to the device, and then it's saying, okay, based on the decision tree of like, did it respond or not respond? Did it give me a reject or did it send me weird value back? Was the field set this way? It's got a decision tree where they basically walk down to say, okay, I think this is FreeBSD, not OpenBSD because of this, that, and the other thing. So if you want to think of what I'm doing kind of like I'm trying to get firmware versions the way someone like Nmap is trying to get operating system versions, then you could say that it would benefit me to send a bunch of weird packet types and then see how things are responding to me. And based on those quirks of particular vendors and particular chip versus chip changes, then that'll give me some indication of which chip I'm actually dealing with. So there's a whole bunch of other packet types. These are the ones that are currently like supported in the code that I've already released. So I just want to give you like a sense of what it means to send a weird packet type and why that might be useful to you. So I'll pick on LMP features extended request. Again, not great documentation. You send it, a request, you get back a response. Now, these feature requests are basically bit masks. So it's a bit mask of a whole bunch of features that the device actually supports. So does it support role switching, like from master to slave and slave to master? Can they switch roles? Does it support sniff mode, park mode, etc.? But in the feature mask, they knew they were going to run out of bits. So they got 64 bits allocated when they started Bluetooth, and they knew they were going to run out. So bit 63 is saying, by the way, I have more features than I can tell you here. Go check the next 64 bits or the next 64 bits. So basically, they've got additional what they call pages. Page 0 is the first 64 bits. Page 1 is the next 64 bits. Page 2 is the next 64 bits. So these are all the new features, like this one, ping. So just like sending a ping packet down at the lowest layers of Bluetooth, that has to be said specifically, I support ping. But then the question is, well, if it says it supports ping, can you try the ping? Does it respond? If it says it supports it, what if it doesn't respond? So you can use all of these features as like a way of saying, you say you do this, but let's see if you actually do. But what we're interested in is that there's this 3 fields of this packet, and features page says the LMP features request extension portable data unit contains a features page index that specifies which page is requested and the content of that page for the requesting device. So first of all, there's this common theme of like, they will send like, hey, by the way, here's my features, what are your features? So it's saying the feature request is actually a, hey, here's my features, but also tell me your features. But then the features page is saying for page 0 or page 1 or page 2. So I want you to tell me your features for page 0, 1, or 2. By the way, this max supported page, by the way, I only support pages up to 1. So don't ask me about anything past page 1. But the thing is, it says pages are numbered from 0 to 255 with page 0 corresponding to the normal thing. So none of the specs support, 255. They're just saying you've got a byte. Obviously, the index could be index 0, index 1, index 2, index 3, index 4, but the spec doesn't support anything past 2. And the device may say, my maximum is 0. So what happens when you send a device, please give me your features page 3 or 4 or 5 or 255? Well, what I've seen happen is that the device can do the correct thing, and it can say like, no, I don't have any features at page 255. Here's some zeros for you. Or it can, just drop the request and never respond. But what I also see is some devices fall over and crash, and other devices, they send me back what looks like uninitialized data, possibly from the heap. So maybe they're actually like leaking information when I start going past the bounds of what they actually expected. So this can turn into an info leak type vulnerability and other things. So yeah, this is just the point of figure out all the types of things you can fire at something, figure out how to fiddle with them, and then send those out, and then do the analysis afterwards. So how do I send these kind of custom packets? Well, 2020 and 2022 brought us SvenTooth and Bracktooth. So Internal Blue was the first tool from the TU Darmstadt people, but that has very poor documentation, and so basically I went with SvenTooth. SvenTooth only does Bluetooth Low Energy. It puts a custom firmware on a Nordic chip, and then you send a packet to the Nordic chip, and then it just sends it for you. Bracktooth puts a custom firmware on a ESP32 chip, and you send a packet to it, and it just sends it for you. So one is in Python, one is in C, and they let you create arbitrary packets. Now, here's the point where I have to actually admit that although for this particular thing, the packet combos and the weird and the malformed stuff, I've collected a bunch of data, but I haven't actually analyzed it yet. And that's because I'm not really happy with this data yet. Because basically, I have a particular bias in that I think the best possible toothprint, like my version of what the best possible toothprint is that I send you packets and I get the responses back and like it's definitive, but it's also fast and it's the minimum number of packets. Do I send 2 packets, 3 packets? What is the minimal possible set that I have to send? And right now I've got all these things and I've got all these data, but I need to actually analyze like, okay, I could send you 10 packets and take like 3 minutes to get this toothprint from you. But what is the actual, like, what is the minimum possible combination of like these 3 packets are the ones that actually like give you 90% accurate data? So one, like I'm trying to figure out what the minimization is. There's actually some academic work that I think that I can use for that. And so that's part of why I didn't want to just ad hoc it when I think I can do something rigorous. But 2, there is some limitations on Bracktooth and SvenTooth, and that each of them adds about like 5 seconds of overhead. So I start them up, they get going, and then they send the packets, and then they're done. Then I send another packet, and then they're done. So 5-second overhead for each of those. I mentioned it earlier, I like to set my sniffers up over freeways. And so when a device is driving past, you have very limited time. More to the point, like my best case scenario is I'm driving on the freeway, and I want to catch like all the Bluetooth traffic from the people going the other way, and I want to tooth print all the people going the other way. So that means I've got order of magnitude a couple of seconds maybe in which I'm in like Bluetooth range, and then I'm going past. So like just a couple of seconds. So right now, although this is great for like static targets like yourself, this is not great for drive-bys, which is what I'm really kind of interested in. So also, it's good to like actually, before we try to do this a little more rigorously, I want to have like known truth as well, so I can say like, I've collected these devices, we guarantee that these are the right chips on them, and so now we can know correctly like what is the minimum set that gives us the accurate data. All right, tooth printing by manufacturer-specific data. This could be 100% passive, or it could be semi-active. So both Bluetooth Low Energy and Bluetooth Classic, we have a type of data called manufacturer-specific data. And this data is supposed to be essentially like a 16-bit field that says this is the company ID. So we've got another company ID, potential opportunity for silicon chip makers. But then the rest of it is all whatever they want. And so this particular data type is used for things like iBeacons, which is like, if you've ever heard back in the day, people were trying to like track you indoors in like, department stores and stuff like that, and figure out like how long you were spending in the shoes section and how long you were spending in the pants section and stuff like that. iBeacons was this Apple protocol where they basically spec'd out and said, you shall put the manufacturer specific data as Apple, and then you shall put like the 16-bit value, 128-bit value, and then you change the values for your different stores around the world and stuff like that. So iBeacons are pretty commonly used. Unfortunately, one thing is that the spec doesn't say what endianness the 16-bit data should be in, and so we see people going big endian and little endian. This just to say that really annoyed me, and I was wondering like, why did the spec not say that? And it turns out they did say that in the 4.0 spec. They refactored their spec in 4.2, put it in some other place, and they lost it. So here's the actual data. So top vendors, Garmin, again, probably just due to my bias of car traffic. Apple, because iBeacons and stuff like that. But that's Apple in the wrong endianness. Like Apple has an official Bluetooth ID that is assigned, and it is 4C, like just 4C, not 4C000. So the endianness is wrong here. Qualcomm, but we see that both with like Samsung and Apple. Samsung has wrong endianness and correct endianness. And Broadcom, and Samsung also just has some random value that I have no idea why they're using. But anyways, Bluetooth Classic, we have about 50-50 here in terms of like silicon makers versus non-silicon makers. So again, going back to the notion of if the company says that it's Shanghai Mountain View Silicon Company, it's probably not, someone else. It's probably using that silicon. Bluetooth Low Energy, on the other hand, and I can see based on this that it says I have 9.5 million data points. Bluetooth Low Energy is where you should actually see the iBeacons. I shouldn't have said that on the Bluetooth Classic slide, sorry. This is, iBeacon only exists in Bluetooth Low Energy. So this is clearly non-deduplicated. That means I have 9.5 million raw data points of devices saying, hey, I'm Apple. And some of those are Apple devices for sure. Those are like just iPhones and Macs and stuff, but a lot of them are actually like Tesla actually does an iBeacon out that says like, I'm an Apple device. It's just using this format that Apple has specified. All right, tooth print by GAT. This is going to be our last tooth of the day because I have like 7 more that I can't cover. So this is the last one. This is active, or at least it's supposed to be active. If you want to do the best case, this should be active. I'll compare against some past work. All right, so GAT is the generic attribute profile. It's not a protocol, it's a profile, which runs on top of a different protocol called attribute protocol, which is AT. So it's basically just this thing where you've got values where you can read and write basically arbitrary data. It's mostly used in Bluetooth Low Energy, but it can be used on Bluetooth Classic. And theoretically, the types of data I want to know about, like chip version and firmware version, can all be received directly through GAT. So, is this the ultimate tooth printing mechanism? Let's find out. So, if you pull up a Bluetooth scanner on your phone, there's lots of things you can just grab on your phone, and it'll say like Bluetooth scanner. I like Light Blue and Blue Fruit Connect, and actually the new one that I found that is the best is BT Inspector. BT Inspector is my new favorite. But yeah, you pull them up and they'll show you something like this. They'll show you a name or they'll say this device has no name. So this was some random one called 047 Instacart 1. And the information it has, you can see that I've got individual device information by way of serial number. That should be unique to the specific device, so I could track this Instacart 1 thing anywhere in the world. I've got model information. It's a ZD621, whatever that is. I've got manufacturer name, Zebra Technologies, so between the model number and the company, I can probably figure out what it is now. And I've got firmware revision and software revision, so that is exactly what I want, right? This should theoretically tell me if I knew that a firmware revision corresponded to, some vulnerable silicon, that would tell me exactly what I want. So this particular thing for this Instacart thing, I was in a Wegmans and I saw it, and it turns out it is a Bluetooth-based receipt printer. Okay, cool, whatever. On the other hand, with GATT, you can get a whole bunch of nothing. So that was like the best case scenario. This is the average case scenario. You see something called ID 205L, and it tells you, hey, by the way, 0AF6, 0AF7, 0AF2, and 0AF1. Those mean nothing to me right now, and maybe in some future world they'd mean something to me, but right now they mean nothing to me. So this tells me nothing I want to know about. So also, GET is not great from my particular biases if I want to be able to collect stuff while I'm driving past things, because GET is pretty slow, so not always the best thing. Now, I will tell you that I think this is this $30 knockoff Apple Watch IDL 205L. I say based on name print. Unfortunately, name print is not one of the things I'm going to have time to talk about, but it's basically a regex of here's some names and I Googled it, and so I think that these correspond to the devices. So there's been some prior work using GATT to try to figure out what devices are, but now here's where my notion, why I'm making up a new name of tooth printing instead of fingerprinting, because different people mean different things by fingerprinting. So this first piece of work in 2019, they actively connected to BLE devices. I think this was in France on the subway and places like that. And they just took everything that was in the GATT thing. They didn't do any sort of processing, and they said, that's the fingerprint. Now, their threat model and their focus was user privacy. And so therefore, that fingerprint they were interested in was more like an individual human fingerprint or individual device fingerprint. They were interested in privacy and therefore tracking, and therefore, can I track you and find out which subway stop you get on every day, which subway stop you get off every day. So that's like the privacy, fingerprinting, individual user, individual device type thing. And so they focused on, device type, device model, manufacturer, user's name. These are the information that can threaten the user's privacy. But, again, I'm over here trying to exploit devices. Firmware version is not something they considered, and I think firmware version is the most important thing to consider because I want to know whether something's exploitable, because getting owned over the air is the worst privacy threat. So one of the things that they put that I just wanted to repeat is that GATT is slow. They're saying it takes 6 seconds to connect to some smart light bulb and 6 seconds to connect to a motion sensor. I've seen things take up to 24 seconds when they're just like sitting right next to me. So GATT is slow. So, is GATT the ultimate tooth printing mechanism? Maybe not. It's got some good information, but then again, back to the point of the information, they were looking at the various GATT services or characteristics in this case, like the different types of data that GATT would return. In their data set, 13,000 devices reported a name, and 99% of the time it was possible to get that name back, but then only 835 devices reported a firmware revision string. So they admitted that their data was highly skewed towards iPhones, so basically they had 9,900 iPhones out of that 13,000, and my data is very skewed towards iPhones too because there's a lot of iPhones out there. But basically, if we've got this data thing where it gives me exactly what I want, a version number, a firmware revision string, but if it's only less than 1/4 of the time, then is that the ultimate tooth print mechanism? No. So the theme here is there are many teeth to a tooth print, and you need all the data possible. You can't just rely on any individual piece of data. Now, there's one other thing that tried to use GATT for fingerprinting, but they did it semi-passively, and they claimed that it was, no, I'm not going to get into it. They basically just scanned passively, just like those phone apps. But unlike those phone apps, you click into an individual device that you see, and now it goes out and it queries and it gets all the GATT information. And it says, give me your device name, give me your firmware string. They didn't do that. They only said whatever's passively advertised. And so some of the Bluetooth Low Energy advertisement will give you the top layer GATT information without you needing to ask for anything more. So they just did the basics there. But so their kind of fingerprinting was not like an individual device fingerprinting, because you can't possibly get that by not getting all the information. They just said, this is more like a model fingerprint. And so I can see that there's an iPhone here and there's a Samsung Galaxy here. And so again, that kind of fingerprint, not even close to what I want and not even close to what you might be interested in for like the privacy threat model. But what was super interesting about their work, and that I want to use this data a little bit more in the future, my current stuff doesn't include this, it doesn't publish it in the repository, but they gave me permission to publish it. So in the future, after I have a student update some of my code, they went and scraped all the Android applications. So you know that like a common way that you're going to interact with a smart device is you're going to have like an app on your phone and then you're going to connect to the device. So they went and scraped a bunch of Android applications and then tried to do static analysis to figure out like what are the GAT characteristics, what are the GAT UUIDs, what are these 128-bit values in the Android app that they also saw advertised by a Bluetooth device. And therefore, they could make a correlation of like, you know, here's my Roomba and here's what it says for Bluetooth, here's my Nest camera and here's what it says for Bluetooth, and they can see like the Roomba application has that statically in the decompiled Android application, and the Nest app has it. So that is going to be super useful for getting backwards from random device with random number that I have no idea what it is, back to, oh, well, at least I know that's that Android application from that company, so maybe it's probably this kind of device. So just for completeness, I'll tell you that my GAT printing thing is using GAT tool from Bluesy. It's deprecated. It's not even included in the latest versions of Linux Bluetooth stuff. You have to go re-enable it and recompile stuff. But I used this because, one, it was pretty much what I needed. I just needed to change it to be a machine parsable output so I could put it in my database. And two, if you try to go out there and use just like high-level APIs like the Linux people want you to use these days, it's going to try to do like full connection and pairing. And you won't be able to do that with most devices without the PIN codes and all that kind of stuff. But you don't actually need to do that for GAT. You can do this unauthenticated. You can get all this information unauthenticated. So you have to use the lower level APIs to get all the information. So just some quick anecdotes of chip-specific things. So GAT has these 128-bit UUIDs for services and characteristics. They're like nested under each other. Service is like some high-level functionality, and characteristics are things that are read or written. So Texas Instruments has an over-the-air firmware update service from GAT. So basically, some devices from Texas that are using Texas Instruments silicon, you can just send them over the air. Here's your firmware update. And so Bleeding Bit, that Armis thing from 2018, they were the first ones to ever do like a typical buffer overflow exploit arbitrary code execution. But they also just bundled in with that. And by the way, Aruba was using TI chips, and they just put like some security by obscurity thing in front of their firmware update thing. So if you send a magic number to the device, great, you just opened up the firmware update interface, and it's got a completely unauthenticated firmware update. Just ship it the entire bundle of arbitrary code you want it to run. So I expect that all of these sort of things that have firmware updates over the air are generally going to have problems. So we've got Nordic. It has UART via Bluetooth, so Universal Asynchronous Receiver Transmitter. Serial port, so it's got serial port over Bluetooth. It's got insecure firmware update. They call it legacy firmware update compared to their new secure firmware update. So I call it insecure firmware update. It's architecturally designed to be insecure, not require authentication. If you see a Nordic device showing that, again, you don't need to do arbitrary code execution bugs. You just use the architectural feature. Cambridge Silicon Radio, they've got an over-the-air update. So again, just these are magic numbers where when I see them, I can say, that thing's probably using Cambridge Silicon Radio silicon, right? I don't need to, I can say it's a company, but probably no one in the world has randomly come up with the same number or decided like, hey, I think I'm going to use the Cambridge Silicon Radio firmware update UUID. Silicon Labs, same thing, and even down to the module makers. Layered, which is a module maker mostly used in cars, they have a virtual serial port. You see the magic number, you know that it's using Layered, and from Layered you can figure out the couple subset of chips that they use. So magic numbers imply manufacturers. Manufacturers, when they are silicon makers, imply silicon. So there's my stats. All I want to say about this is that you can see that my data is Apple biased, right? You can see that Apple services, the top level service is 10,000, and then the next level down is Bose, which is only 843, right? So clearly my data is skewed by a bunch of Apple devices. Apple services, Apple characteristics, and again, big jump down from 10,000 to 1,600 for the things that actually have firmware revision strings. Putting it all together, there are many different data types that all make up a tooth print. And even if wireless weren't a lossy type of thing, not every device is going to have every data type. but that's what makes it beautiful. The tooth print of any individual device is unique and special, and it's great, and I love collecting them all. So tooth printing code is now available, or it's been available for a bit on this link. But really what I want today is I want to have the call to action for all of you to look at Bluetooth. I want you to join me, and together we will rule the Bluetooth galaxy. That was for those people over there as well. Oh wait, they're done though, so whatever. All right, Bluetooth is cool. Bluetooth is under-researched. I didn't mention it in this talk. I mentioned it in other talks. There's like 20 silicon makers. There's more than enough room for all of us to like specialize in one particular silicon maker and things underneath that. So, I'm putting together a blue crew, and basically I need people to continue to work on this because this is only 25% of my time. I need to get back to making my free classes. I'm working on a RISC-V assembly class right now, so I like doing this work, but I need to keep my focus on the nonprofit. So if you're interested in this kind of thing, like I'm taking students from local colleges and stuff like that and saying, okay, you're going to work on this piece, you're going to work on that piece, and we're trying to like keep the ball rolling until I can pick it up again as part of my 25% per year. Now, to that point, doing research in some new area requires reading the related research, right? So I have this, this darkmentor.com/bt.html, just like I used to do with UEFI and firmware. I put together, here's the last 20 years of all the Bluetooth research that matters, essentially. Like there's lots of little like blog posts by people saying introduction to Bluetooth. Those don't matter. Read the actual academic research, read the conference papers, read the highly impactful things. So there's about 200 papers there, but you don't need to actually go read all 200 papers. I have a separate talk that I only did once, but it's basically statistics from this wiki showing that like in the Bluetooth security research space, there was, well, I mean, I'm the last slot, so I'm going to keep going, but I'm almost done. In the Bluetooth security research space, there was like a peak at the beginning, and like it completely died by 2006. And like I saw that, I was around back then, and like people were doing a ton of research, and then it was dead. And then like things only really started picking up, again, like 2013 and stuff. And now we're like in a massive spike of like all sorts of stuff going on, and so it's pretty cool. All right, that's my talk. Bluetooth research is cool, but again, open security training is cooler. That's what I spend my time on. So we are going to be putting together Bluetooth classes, myself and my wife. She's the Bluetooth expert. I'm just catching up to her at this point. But basically, you can already go there and do all sorts of classes on assembly language and reverse engineering and vulnerability hunting and TPM here soon. We will create Bluetooth classes, and that is also, I'm going to use my recruits from the Bluetooth classes to keep developing the tooth printing tools. But until then, go off and take a class, and we're always looking for volunteers to teach classes. I'm sure all of you know all sorts of stuff that I don't know. We'd love to have you teach some other people. With that, thank you.